Okay, so what do you think a skyscraper, a honeycomb, and the screen you're looking at right now all have in common? Well, they're all built using the same simple blueprint. Polygons. Today, we're going to decode the language of these fundamental shapes, the ones that literally structure our world, from the absolutely epic to the everyday.
Just take a look at this bridge. I mean, it's strength. It's not magic, right? It's math. See all those interlocking triangles? That's what creates a structure that's just incredibly strong and stable. So you see, polygons aren't just some abstract idea you find in a textbook. Nope, they're like the invisible skeleton that holds up the world all around us. So let's learn their language.
All right, so here's our game plan for today. First up, we're going to start with the absolute basics. What officially makes a shape a polygon. Then, we'll get into how we name them, their family names, if you will. After that, we're going to look inside these shapes at their diagonals. And finally, we'll uncover the universal rules that govern their angles and get into some really special cases. Sound good?
Okay, section 1. Let's lay the foundation. What are the non-negotiable rules for a shape to even get into the exclusive polygon club? What's the secret password?
So this definition right here, it's got 3 key rules baked right in. First, it has to be closed. Just think of it like a fence with no open gates. Can't have any gaps. Second, it's a plane figure, which is just a fancy way of saying it's flat, like a drawing on a piece of paper. And finally, and this is probably the most important rule, its sides must be straight line segments. So yeah, curves need not apply.
And here we can see those rules in action, side by side. Over on the left, you've got your valid polygons. See? All closed in, all straight sides. But on the right, well, we've got the imposters. This one here, it breaks the straight side rule. This one, it breaks the closed figure rule. It's got a gap. And this one, well, that's just a squiggle. Definitely, absolutely not a polygon.
Okay, but not all polygons behave the same way. The first big split in the family tree is between convex and concave. A convex polygon is kind of well-behaved. All of its corners point outwards. But a concave polygon, it's different. Just like the name suggests, it has at least one corner that caves in. It creates what we call a reflex angle, which is just an angle that's wider than a straight line. And this is a great way to see it. Look at the shapes on the right. They've all got that indent, that cave-in. Now here's a really simple trick to test for this. Try connecting any 2 points inside the shape with a straight line. If you've got a convex polygon, that line will always stay inside the shape. But with a concave one, like you can see with these dotted lines here, that line can actually go outside the shape. Pretty cool test, right?
All right, so now we can spot a polygon out in the wild. We know the rules, but what do we call it? Let's get fluent in speaking geometry.
So a polygon's first name almost always comes from its number of sides, and we usually use a Greek prefix. You already know the common ones for sure. A 3-sided shape is a triangle. 4-sided is a quadrilateral. But that pattern just keeps going. Penta means 5, like the Pentagon building. Octo means 8, like an octagon, a stop sign, and so on. This chart here lays out the most common members of the polygon family.
Another way we can think about this is by organizing these shapes using set theory. So in this Venn diagram, that big rectangle, the one labeled P, that represents the entire universe of all possible polygons. And then inside that universe, we've got these smaller, more specific sets of shapes.
And check this out. Notice how the circle for triangles, T, and the circle for quadrilaterals, Q, are totally separate. They don't overlap at all. In set theory, there's a word for this, disjoint. But really, it's just a formal way of saying something you already know intuitively, right? A shape can't be a triangle and a quadrilateral at the same time. It's got to be one or the other.
Okay, so we've defined their boundaries, we've given them names. Now it's time to venture inside the shapes themselves and check out their diagonals.
So what exactly is a diagonal? Well, think about the vertices, the corners of the polygon. A normal side connects 2 corners that are right next to each other. They're consecutive. But a diagonal is a special line that kind of plays leapfrog. It connects 2 vertices that are not next to each other, skipping over at least one corner in between.
And this slide just lays it out so clearly. A triangle, well, it doesn't have any non-consecutive vertices, so it's got 0 diagonals. A quadrilateral has 2. A pentagon has 5. And look at the hexagon. It has 9. Whoa. You can really see that as the number of sides goes up, the number of diagonals grows way, way faster.
You know, counting those diagonals in the hexagon was already getting a little tricky. Can you imagine trying to do that for a 20-sided polygon? I mean, no way. Luckily, we don't have to. There's a really elegant formula that does all the heavy lifting for us.
And here it is. This is that awesome formula. To find the number of diagonals, which we'll call d, you just take the number of sides, n, multiply it by n minus 3, and then you divide that whole thing by 2. I know it might look a little complex at first glance, but trust me, it's an incredibly powerful shortcut.
So let's put it to the test, right? Let's try it with a triangle where n equals 3. So we follow the formula. We get 3 times, well, 3 minus 3 is 0. So 3 times 0 is just 0. And 0 divided by 2 is still 0. Bam! The formula perfectly matches what we already saw. It actually works. All right, for our final section, we're shifting gears. We're moving from the lines that form polygons to the angles they create. And this is going to unlock a whole new set of rules and reveal some very, very special shapes.
Now this right here, this is one of the most powerful rules in all of geometry. Seriously, this theorem is like a cheat code that lets us find the sum of all the interior angles for any convex polygon, and all you need to know is its number of sides. The formula is so simple. Just take your number of sides, n, subtract 2, and multiply that result by 180. That's it.
So let's try it out with a hexagon, where n is 6. Okay, so we take 6 minus 2, that gives us 4. Then we just multiply that 4 by 180 degrees. And what do we get? 720. And here's the crazy part. It doesn't matter how weird or skewed or stretched out that hexagon is. Its 6 interior angles will always add up to exactly 720 degrees. That's just a universal law of geometry. Okay, remember those special polygons I mentioned earlier? Here we go. A regular polygon is basically one that's perfectly symmetrical. It has to meet 2 strict conditions. First, it's got to be equilateral. That means all its sides are the exact same length. And second, it's got to be equiangular, which means all its interior angles are equal. Think about a perfect square. That's a perfect example of a regular quadrilateral.
But what about the angles on the outside of the shape? Well, this is where things get surprisingly simple. And I mean really simple. For any convex polygon, it doesn't matter which one, if you add up all its exterior angles, they will always, without fail, sum to exactly 360 degrees. It's like this constant of the universe, whether you have a triangle or a 100-sided polygon. And if you have a regular polygon, it's even easier. You can find each exterior angle just by dividing 360 by the number of sides. How cool is that? And that brings us to our final concept, and honestly, it's one of the most visually stunning, the polygram. So what is it? It's what happens when you take a convex polygon, one with 5 or more sides, and you just extend its sides outwards until they cross each other, creating a star. The most famous example, of course, is the pentagram, which is born from extending the sides of a regular old pentagon. So, think about it. We started with just a few basic rules, and from there, we built our way all the way up to complex formulas and these beautiful star-shaped figures. That's the real power of the polygon blueprint. It's a simple set of instructions that generates all the incredible complexity and structure we see in our world. So the only question left for you is, now that you speak the language, what hidden shapes are you going to start discovering all around you?